Hello, here's a quick walkthrough for the Spring 2018 Exam 1 for MA 261. It's been about 4 months since I've looked at this specific exam form. In fact, all of the Exam 1s I'm recording over winter break. So hopefully it will go well. I mean, I worked on them a bunch, so it should still be in my head. Let's see how it goes. Let's identify the quadratic surface defined by this thing over here. We see that it's not really in a form that we're used to identifying, and in this case, we can complete the square. So we're rearranging things a little bit. We see that we have x squared minus 4x minus y squared plus z squared is equal to 4. We don't need to do anything to these guys. This is fine, but we really would like to remove or rearrange our x component. And completing the square, all we have to do is add 4 to both sides, and that will give us x squared minus 4x plus 4, blah, 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 is equal to 8. And this we can factor to x squared minus 2. And so putting everything back in, minus y squared plus z squared is equal to 8. And we see that this is just an equation for a hyperboloid of one sheet. I'm sorry, this is not right. X minus 2 squared. There we go. A hyperboloid of one sheet that's been shifted a little bit along the x-axis and widened out a little bit. So hyperboloid of one sheet is our answer. If L is the tangent line to this curve R of t at this point, we need to find the point where this tangent line intersects the xy plane. So our tangent line is just going to be r prime of t, or at least we're going to need to find r prime of t to get things going. We see that r prime of t is 2, 2t, 2t, and this doesn't really help us because we don't know what value t we're looking at, and so in order to do that, we have to figure out what value of t satisfies this ordered triplet here that we're dealing with. And so all we have to do is solve any one of these equations. In this case, I'll solve 2t minus 1 is equal to 3, and this is true for t is equal to 2. So we know that our r prime is really r prime of, not t, that's exactly what I didn't want, of 2 is the one that's going to be relevant for us. So 2, 4, 4 is going to be the slope of this tangent line, and we already know that a point that is on this tangent line, or the point that our tangent needs to be tangent to, is 3, 4, 2. And this is just how I like to write the parametrizations of these things, 2, 4, 4. And that's a t in there. So for every unit t, we want to move 2, 4, 4. And now we're looking for where this line intersects the xy plane. Well, that's going to be true for z is equal to, not 1, z is equal to 0. There we go. And so we can solve our z component down here to figure out what value t satisfies this. So 2 plus 4t is equal to 0, or t is equal to negative 1/2. So when t is equal to negative 1/2, get rid of all this, negative 1/2, we are going to get an ordered pair of, an ordered triplet of 3 minus 1 and 4 minus 2 and 2 minus 2, which will simplify down to 2, 2, 0. Okay, let's let our velocity vector equal the integral from 0 to 1 of all this jazz in here, dt, and we're computing the magnitude of v. So let's figure out some more stuff about v. This looks like an integral that we can take pretty easily. We just have to do it individually with respect to all of our components. Integrating 1/2 from 0 to 1, we are going to get t over 2 on 0 to 1, which is just 1/2. For our y component, we will get t to the 4th over 2 on 0 to 1, which will give us another 1/2. And for our last component, we will get t squared over 2 minus t cubed on 0 to 1, which will give us 1/2 minus 1, so negative 1/2. And so v itself we can form as 1/2, 1/2, negative 1/2, where the magnitude of v is going to be root 3 over 4, or root 3 over 2. Let's find the area of the triangle with these vertices. So later on in the course, when surface area integration comes up, you can actually do this another way. And I got into the habit of only doing it the surface integral way, but there's a much easier way, and it's just the cross product, because we know that the cross product of two vectors is going to give us the area of the parallelogram span between those vectors. And if we take half of that, we have the triangle formed between those vectors. And so then all we need is a vector that points from Q, in this case I'll just use Q, from Q to P and from Q to R, and we need to cross those and divide by 2. So a vector that points from Q to P is going to be 1, 3, negative 1, and a vector that points from Q to R is going to be negative 1, 2, negative 3. And so taking our cross product, we will get, let's see, negative 9 plus 2 is negative 7. 1 plus 3 is 4. And 5. Okay, and so the magnitude of this whole thing is going to be over 2 is going to be root 49 plus 16 plus 25 over 2, which will work out to, let's see, 49, that's not a 9. 49 plus 16 plus 25, 11 plus 9, 20, 4, 5 is 90. So root 90 is the same as 3 root 10, and 3 root 10 over 2 is answer choice B. Okay, the level curves of f of x, y is all this stuff, are what? So when we're trying to solve these questions, we just set f of x, y, our z value, equal to some constant k, and we say that that's equal to root x squared plus 4y squared plus 4 minus x. So we can rearrange this as k plus x squared equals x squared plus 4y squared plus 4. We can square this over here. K squared plus 2kx plus x squared is x squared plus 4y squared plus 4. We can cancel out our x squareds, and now we should have this in a form of something that we can identify. So if this were to be an ellipse or a circle, we would need an x squared and a y squared, which we do not have. It's also the same for hyperbolas. We would need to have an x squared and a y squared term. And the same thing over here. We never have an x squared term no matter what k is equal to, and so D is wrong. And in fact, we're just left with a paraboloid, and we can kind of do some transformations here, and you'll see it'll still be the same kind of thing, the same kind of shape. If we get rid of any constants and divide out any there's a constant too, and divide out any coefficients, that's the word I'm looking for, and we're just left with x equals y squared, which we know to be a parabola. Let's find the length of this curve from t between 0 and 1/2. So we know that this is going to end up being the integral from 0 to 1 of the magnitude of r prime of t dt. And all we have to do is find this r prime of t. R prime of t is going to be 4 cosine t, 3, 4 sine t. And this magnitude is pretty easy to see. We don't even have to work it out. It's going to be the square, well, sorry, I am working it out, so, but I'm taking a little shortcut because 16 cosine squared t plus 16 sine squared t is just going to be 16. And so the square root of 25, which is what we have here, gives us 5 for the magnitude of r prime of t. And so since we're doing the integral from 5, from 0 to 1, we get d as our answer. It's, wait. I thought so. There was something wrong. What did I do? Oh, there it is. I'm not even going to cut that. I'm going to leave that in there because that's a very legitimate and stupid mistake. I did an integral from 0 to 1. What I meant was an integral from 0 to 1/2. So there is our 2.5. Okay, we have a particle moving with some acceleration. If at time t equals 1, it has a position of that and a velocity of that. We're looking for the magnitude of the position at t equals 2. So we know that for these problems, in order to get from acceleration back down to position, we have to do some integration and take into account the constants or the initial values that they're giving us. So the integral of each of these components is going to give us 6t, 3t squared, and 0. And this will be our v of t, but we need to make sure that this agrees with our initial velocity. So our initial velocity at t is equal to 0 is 0, 0, 1. So we see that plugging in 0 for t, x checks out, y checks out, but we're going to need to add a constant of 1 over here so that that also checks out. And then finding r of t, we're going to get 3t squared, t cubed, t equals, not r prime, r vector of t. And finally, we just need to make sure that this agrees with our initial position, which is 2, 1, 2 for r of 1. Well, when t is equal to 1, this thing is equal to 3, so we need to subtract 1. When r is equal to 1, this is 1, so we need to do nothing to it. And over here, we need to add a 1. And we are looking for the magnitude of the position vector, excuse me, at t is equal to 2. So plugging in t is equal to 2, we will get 11, 8, 3 equals r of 2. And the magnitude of this is just going to be the square root of 121 plus 64 plus 9, which, if I remember correctly from a couple months ago, is the square root of 194. I don't really feel like doing all that math, but that does check out. Okay, question 8. We are looking for the second order mixed partial derivative of this thing right here at pi and 1 for x and y. And remember, it doesn't matter which order we do this in. If you feel like finding fyx, you should get the exact same thing. And in fact, just to prove it, we will do that. We will find fy first. This is just going to be, let's see, 2x squared y cosine xy squared. And then we need to find the partial derivative of this with respect to x, which is going to give us 4xy cosine xy squared minus 2x squared y times, let's see, times y squared sine xy squared. Okay, so it's a big one, but it's going to simplify down a lot because we see that both of these things in here for our trig functions, it's going to simplify down to pi because we're going to get pi times 1 squared, so we'll have a pi in here and a pi in here, and that's important to recognize because the sign of pi is 0, so this entire section over here is equal to 0. And then moving back over here, we will see that this is just 4 pi times the cosine of pi, which is just -1, so our answer is -4 pi. let's let f of x, y, and z be a function that's differentiable at 1, 1, 1, where the partial derivative of f with respect to x is -6, and with respect to y is 2, z is -1, blah, blah, blah. And here's where it gets weird. We have a function gamma vector of t that's composed of x of t, y of t, and z of t. And let's see, they're telling us that gamma of 0 is 1, 1, 1, and the partial derivative of gamma with respect to t is 3, -3, 1. Okay, so this is an extremely roundabout way of doing the multivariable chain rule. So we're looking for the derivative of f with respect to t, where gamma is composed into f. And all we need to recognize is that this is a place where we can apply the multivariable chain rule because we have a function composed into another function. And we will see that dt of f of gamma of t is just going to be, let's see, fx, sorry, yeah. Yes, so sorry, f is a function of x, y, and z. So fx gamma t plus fy. Well, so see, it's hard to write this out because this is not a very normal way of doing things. Usually we're not given vectors like this, but really we want the x component of gamma with respect to t, and over here we want the y component of gamma with respect to t. No, this is x. And really, I've never actually written out what happens for this problem, which is kind of an issue. Also, my gammas are pretty bad, z with respect to t. But that's really because once you figure out how this problem works, you see that all we're doing here is multiplying this by this, multiplying that by that, and adding that multiplied by that. Because those are the things that fill in all of our blanks, which is this is a remarkably weird way of asking one of these questions, and it's very unlikely to come up again. It never came up in fall 2019. They seem to be, but you know, they seem to be asking weirder and weirder questions lately. So not really sure, but I wouldn't sweat it too much if this doesn't fully click. It's definitely still doesn't for me. So multiplying all this, we're going to get -18 minus 6 minus 1, which is just going to be -25. And we're done. Okay, which of the following is an equation for the tangent plane to this explicitly defined surface at this point? So we know that when our surface is explicitly defined like this, our tangent plane is going to be in the form z minus z naught equals zx, x minus x naught plus zy, y minus y naught. And we can immediately start filling some things in. We know that x naught, y naught, and z naught are just the points that we're finding our tangent plane at. So this is going to be pi over 4. X naught is 1 over root 2, and y naught is 1 over root 2. Okay, now let's take a look at our zx's and zy's. Zx is going to be 1 over 1 plus x squared plus y squared squared. Yeah, and sorry, we need to do the chain rule on that, so we're going to end up with a 2x on top, and over here we're going to get 2y over 1 plus x squared plus y squared squared. So these things are kind of scary at this point, but when we plug in these values over here, it should get a lot more simple, because we will see that this is going to be equal to 2 over root 2 over 1 plus, let's see, x squared is going to be 1/2, y squared is 1/2, so that's 1 squared, which is just 1. So over 2, and we can simplify this down to 1 over root 2. And so this guy also, because our x's and y's are equal, this is also just 1 over root 2. And so now that we have both zx and zy, we can plug things in, and we should be able to get an answer. So we still have z minus pi over 4, but that's now equal to 1 over root 2 x minus 1 over root 2 plus 1 over root 2 y minus 1 over root 2. So let's multiply everything by root 2 over here. So we can get rid of this and get rid of that and take this whole thing over here and multiply it by root 2. And we are left with a much simpler right side of our equation. This is just going to be x. So this whole thing can be rewritten as root 2z minus root 2 pi over 4 is equal to x plus y minus 2 over root 2, which is surprisingly equal to one of these things, even though at this point it looks like none of them, although you could recognize that the only answer with a root 2z is this guy up here, and that does turn out to be our correct answer, but let's just make sure. So let's move root 2z over, and so we'll move root 2z over here, we'll move this constant over here, and we will see that in fact this does give us answer choice C. We will get x plus y minus root 2z, and that's equal to, root 2, 2 over root 2 minus pi over 4 times root 2. Make sure that this is separate. And what they do here is take out a root 2. Really this 2 over root 2, if we multiply everything by root 2, this is actually just root 2. And so we can factor that out, and we will get our 1 minus pi over 4, like they have over there. Let's find the absolute minimum value of that guy on that region. Oh, sorry. The absolute minimum is 2, and they're looking for the absolute maximum. Okay, so what we're going to have to do for this, we are given, let's see, this region is some ellipse that doesn't really look like an ellipse, but some ellipse with the center included. So we're not just looking at the outside. And we're looking for the absolute maximum. So we are going to have to check both the outer edge of the disk and the inside, which is kind of going to be a real pain. So first, applying the second derivative test to check the inside, we see that fx is 2xy squared, fy is 2yx squared, fxx is 2y squared, fxy is 4xy, and fyy is 2x squared. And so our matrix that we're going to be working with is 2y squared, 4xy, 4xy, 2x squared. There we go. And I'm going to replace that terrible 4 right there. Okay, so we are looking for some critical points inside this region here. And we see that we will have a critical point if both fx and fy are equal to 0, and that works if x is equal to 0, y is equal to 0 for any values that keep us inside of our region over here. But looking closely at our matrix over here, we know that we're looking for an absolute maximum, and the rules of this matrix are that if the discriminant is greater than 0, if fxx is less than 0, we'll have a max, And if f(x(x) is greater than 0, we'll have a min. But since we're squaring our term here, we can only get maximums. Sorry, not maximums. We can only get minimums out of this thing, because any value y, if we square it, we are going to get a positive number, which will make that critical point a potential relative minimum, but it can never be a potential maximum. And so all of that was actually for nothing, but we had to go through it anyway, because any points inside of our region here can only potentially be minimums. And the sad part about that is that our absolute maximum is going to be on the outside, on the rim of our function. Not our function. Sorry, it's getting late, of our area here. And so since I have forgotten the method that they teach you for exam 1 to kind of go through this, I'm going to use the method that you learned right after exam 1, which are Lagrange multipliers, which are actually much easier in finding this kind of thing. So for Lagrange multipliers, what we are doing is noticing that we have a function that we're trying to maximize or minimize, and we have a function that is our constraint. And we're going to call our constraint g of xy, and we're going to call our function over here f of xy. And to do our Lagrange multipliers, we set fx equal to gx times some constant lambda, and we set fy equal to gy times some constant lambda. And then we can solve this system of equations for a nice relationship between x and y. We can plug that into our constraint and eventually get an ordered pair out of it that we can evaluate. And so going through these motions, we'll see that fx is equal to 2xy squared, and gx is going to be x multiplied by lambda. And then down here, we will get 2y x squared is equal to 2y lambda. So dividing things out, we can divide a 2y out there, and we can divide an x out there. So we see that 2y squared is equal to lambda and x squared is equal to lambda. So we can set both of these equal to each other. We'll see that 2y squared is equal to x squared. And this works out perfectly because we can divide by 2, and we have a nice little relationship that we can use, because we can head back up to our constraint over here and see that for every x squared over 2, we've just learned that we can replace that with a y squared. So overall, we're going to have 2y squared equals 1, and we have an equal instead of a less than or equal to, because we are dealing with only the rim or the boundary of our region instead of the entire region. And so solving this, we'll see that y is equal to plus or minus 1/4. And since we know that y squared is equal to x squared over 2, or 2y squared is equal to x squared. Wait a second, y squared is equal to 1/2. It's equal to 1 over root 2. Yeah, I'm not sure what happened with that. Root 2, there we go. Sorry about that. And then we know that since this is true and this is true, we can plug that value in for y, and we will get 2 times 1 over root 2 squared is equal to x squared. This is just going to be 1/2 times 2 is 1. That's equal to x squared, so x is equal to plus or minus 1. Okay, so now we have 4 different points to check, because we know that x is plus or minus 1. We know that y is plus or minus 1 over root 2. But instead of checking all 4 of these possible points, all we have to do is look at our function here and see that it really doesn't matter, because everything's getting squared in the end anyway. So plugging in both, I really hate this question, if you can't tell. Plugging in both of these, we would get 2 plus 1 squared times 1 over root 2 squared, which is 2 plus 1/2, or 2.5. Okay, finally, let's let z of x and y be a function implicitly defined as a solution to this implicitly defined equation over here that satisfies this whole thing. And we're finding zx at 1, 1. So we know that since we're dealing with implicit partial differentiation, zx is going to be equal to negative dz, or sorry, dz over, no, sorry, I got that mixed up. You need to switch it. So negative d dx over d dz. There we go. And we can find each of these bits individually, and the whole thing becomes a lot more easier. So d dx of this whole thing is just going to be 1 plus yz cosine xyz, and dz is going to give us 1 plus xy cosine xyz. And we can start solving all of these things. We know that z at 1, 1 is equal to pi over 2, and that x and y are both 1. So this cosine of xyz is just going to be the cosine of pi over 2, which is 0. Yeah, so that whole thing is 0. And so all we're left with is negative 1 over 1, which is negative 1. I did not remember that answer at all, and that was kind of anticlimactic, but okay. I guess that's that. Hope this was helpful.